Welcome to Ask and Learn.
In this problem, again, we have a block hanging suspended from a ceiling through a spring. And now we have an applied force that's a function of time, harmonic function, with an amplitude f naught and a frequency capital omega. And we're going to, what are we asked to determine? Determine the equation which describes the motion. Okay, so it's given some initial displacement of 100 millimeters and released from rest. So it's at equilibrium here, so gravity has canceled out in our equations because of the static deflection is offset. So this is our equilibrium, and then we pull it down 100 millimeters and then let it go from rest. All the while this force here is acting on it. So our equation of motion is simply given by this, and once we know this, we can just write down the solution. So our homogeneous solution is here, our harmonic particular solution is here, where the static deflection is f naught over k. Let's see here, the natural frequency is square root of k over m, and that turns out to be 7.75 radians per second. We can find A and B from our initial conditions, and we've basically done that before. So B is the initial displacement, and A is going to be minus the static deflection times the frequency ratio all over 1 minus the frequency ratio squared. And that, in this case, it comes out to be 361 millimeters. Then we can just piece everything back into here and calculate this term here. Since we know what omega is 8 radians per second, we know omega n is this. And so we can see actually that the amplitude of this amplitude here is going to be quite a bit bigger than the static amplitude, and because r is pretty close to 1. So we have 8 radians per second compared to 7.75 radians per second. So that's why this thing here is 361 millimeters compared to 100 millimeters. So we're getting quite a big amplification of the motion because of the frequency of this force. So here's our particular solution, and that's oscillating at the natural frequency, and then our homogeneous, or particular, what did I say? This is our homogeneous solution, and then our particular solution is here, and we can see that that is this is pretty big because this, but this here is pretty big because this is, sorry, this coefficient here is quite big because r is pretty close to 1, and so the static deflection was, let's see here, f naught over k, like little about 1, so 6, about 1 over 30 or something like that. Anyway, it's pretty small. And so then we get this term down here is pretty close to 0. So this gets amplified a lot. And so this is quite a bit bigger than f naught over k, as you can see clearly. Although this is in millimeters. Again, this would be in f naught over k would be in meters. But again, we're getting quite a bit of amplification here because this 1 over 1 minus r squared term here and here. And so that's why these two terms are fairly big. If omega n was not so close to the natural frequency, then they would be much smaller.